Welcome to today's class. Today I want to say a few words about the trigonometry of the hyperbola. The idea is very basic. I want to define the hyperbolic cosine and the hyperbolic sine, but I don't want to define them in terms of the exponential. I want to define them in terms of a hyperbola. Following the philosophy with which one usually encounters the definition of the usual sine and cosine for the first time. When one sees the sine and cosine for the first time, the usual sine and cosine for the first time, one usually sees it in terms of a circle. By opening an angle with the measure of the real number whose sine and cosine one wants to define, and then measuring the adjacent and opposite sides and dividing them by the length of the hypotenuse, which if one works on the unit circle is 1, so that becomes just the coordinates of a point. So in general, today's class is going to be based on a presentation given by Cesar Zarco Romero the previous time I taught this course. So the previous time I taught this course, the trigonometry of the hyperbola was a section that I gave for a student presentation, and Cesar Zarco Romero made that presentation. And today's class is pretty much based on his presentation. Okay, so as I said, the usual sine and cosine of a real number. How does one see it the first time one sees the definition? Well, consider the unit circle, and then one takes the number beta and opens. You see, one traverses a segment on the circle. If beta is positive, one traverses starting in the point 1, 0 and traversing in the counterclockwise direction. And if beta is negative, then one starts in the point 1, 0 and one traverses clockwise, right? And then one traverses on the unit circle a segment of length, the absolute value of beta, and then sees the point where one ends after traversing that segment of length, absolute value of beta. And the coordinates of this point, because since we are working on the unit circle, are by definition the cosine and the sine of the real number beta. And I'm going to do that, but with respect to hyperbola. So these identities that many people use as definitions of the hyperbolic sine and hyperbolic cosine in terms of the exponential are going to become theorems. Okay, so first of all, which hyperbola? I'm going to take this hyperbola, which is a hyperbola that opens vertically, right, as we saw last class. And I'm going to work with the upper sheet. So I'm going to ignore the lower sheet. So here let me also write z greater or equal than 1. Okay. So if you will, you see I'm writing it as some sort of cross section in the YZ plane of the upper sheet of the hyperbola. Okay, so the first thing is precisely by what we saw last class, that for the hyperboloid, for the upper sheet of the hyperboloid, Minkowski's form is a Riemannian metric, well, here as well, Minkowski's form, which in this case it's one dimension lower, so it's Minkowski's form 1, 1, given by this formula. And it makes of this upper sheet of the hyperbola a Riemannian manifold. So this on each tangent line to this hyperbola, it gives you an interior product, an inner product. Okay, so and this we no longer need a proof, right? We pretty much did it already. Okay, and it is with respect to this Minkowski's form that we are going to define the length. So kind of when we measure length, instead of working with you see with the kind of with the Euclidean dot product, we're going to do it with the Minkowski's. And well, how can one define the length of a curve on this hyperbola? Well, I mean, just take the interior product of the velocity vector with itself, right? And the norm, then it's the square root. So just integrate that norm, right? The idea being the same from Calc 1, which is that if you have a curve, then first you think you can approximate the length by taking the lengths of the velocities, right? And then that length of the velocities, which would be kind of the speed at that given moment, or the rapidity at that given moment, multiplied with the length of the circle of the segment, thinking that is more or less the corresponding length, and then add, and then when one takes the sum, one sees that it looks like a Riemann sum that approximates this integral, right? That tends to that integral when you refine the partition of the interval, right? So okay, so the reason for defining it this way is the same from Calc 3 or from even from Calc 2. But now, of course, we with respect to our new dot product, our new way of measuring the length of the velocity vectors, of tangent vectors. Right? Okay. Okay, and then I want to say, you see, now I'm in this situation. So let me draw. So I have my coordinate axis, which are y and z, the y and z axis, and I have the hyperbola, more or less. It's not very nicely drawn, but okay. And then now what I want is you see to start from this point, which now is the point 0, 1, and then if they give me, let's say, a positive real number, let's say then I want to say, you know, to relate this length, but this length measured with respect to the, you know, to Minkowski's form to the coordinates of this point, right? Okay, so what I'm going to do is I'm going to take this point, and then I'm going to parameterize this curve, and then I'm going to look at the hyperbolic length of this curve. So one way to parameterize this one is by seeing this as a function, as a kind of that's writing z as a function of y, let's say. Okay, and then so pick this point, right? So this is the point y0 z0, and something we can do is just take sorry. Here I'm sorry, it's the other way around. I'm writing it as if y y is a function of z. Yeah, sorry about that. And I'm doing that because somehow I'm writing with the vertical picture, not with the horizontal picture. And so actually the cosine of this point is going to be not this length, but this length, this coordinate. This one is going to be the cosine, the hyperbolic cosine. Anyway, I'm getting ahead of myself. So go from this point to this point, and one thing you can do to parameterize is with a curve that goes from, you know, the curve whose domain is the interval 1 z0, so this little interval, and then in the second coordinate, well, it's just s, and then you solve for y. Okay, so that's one way of parametrizing. And well, let's compute this the corresponding length. For that, we need to compute the derivative. So you compute it. It's calc 1, right? So you compute it, and so the hyperbolic length, which I'm going to denote beta of z0, because everything is going to be to depend in terms of z0, because it's an integral. You know, because the curve goes from 1 to z0. Okay, so it's this one. So it's basic computation, right? So it's the dot product is this times this minus 1, right? So this times this gives minus 1, and then you take square root integral of that. Okay, right, and then you see you just perform the operation inside the square root sign, and okay, so you just take a common denominator. Right? Okay, now first the function, you see, we take the positive square root always, which means that this function that goes from the real numbers greater than 1 to the reals, that takes z0 to the integral. That's strictly increasing, right? Because this is always positive for in the interval 1 infinity. I mean the function we're integrating is positive, so the integral is increasing. Okay, so we can define, well, we define the cosine, the hyperbolic cosine of this number to be z0, and the hyperbolic sine of this number to be y0, right? I mean, it's kind of just like in the Euclidean case, one takes this is beta, and then the sine and the cosine of this number are the coordinates. So you see, this we take this length, and the hyperbolic cosine and sine are the coordinates, right? And here, as promised, it's the vertical one is the hyperbolic cosine, right? Because I chose to work with the vertical picture of the hyperbola, not the horizontal one. Right? And I did this because this one is already so naturally embedded in the hyperbolic in the hyperboloid without having to rotate, right? Or switch coordinates or anything. So this will make my life easier later on. I mean, that the cosine is measured vertically and the sine is measured horizontally. Anyway, but so what's kind of the difficulty at this point? Well, is that well, I mean, I would have to argue that this integral, you see, that every positive real number, for instance, is of this form, right? Or you see, or that like when z0 tends to infinity, the integral tends to infinity, so that in this definition I at least cover all positive real numbers, right? So at the moment I don't know that, and well, if you already can see it from this integral, then okay, good. But anyway, I'm going to see it in a moment. But for the moment, it's kind of I know I can make these definitions only for for the betas that are in the image of this mapping, right? Of the mapping that to each z0 associates this integral from 1 to z0. Okay, now let's do some explicit computations. So let's compute explicitly the integral in terms of z0, z0. So look, notice this. This is s squared minus 1. Okay. Well, where can I see, a square minus 1? Well, more or less here, right? But so from this one, from this identity, and these definitions that the tangent is sine divided by cosine, and the second is 1 divided by cosine, we see, well, here we can divide by cosine square. This cosine square, this becomes 1, and here cosine square, this becomes secant square, and this becomes tangent square, and so we see this identity, right? So this identity is pretty much this identity divided by cosine square. Okay, and well, somehow this suggests a change of variable, right? Of making s secant of t. All right. So I make that change of variable, but then since I'm substituting this by a function of t, I also have to multiply with the derivative of that function of t, right? So I compute the derivative. It's quite easy because the secant is this quotient, right? So just chain rule gives me this. So it gives me, you see, this sine goes with, sorry, I have this with one of the cosines. It gives me the secant, and then sorry, gives me the tangent, and then the remaining cosine gives me the secant. Okay, and then minus times minus gives me plus. Okay, so I take this integral and then I make the change of variable. So I obtain this, right? So I have to take secant inverse of z0 and secant inverse of 1, which is 0, right? Which you can see here because secant inverse of 1 is when this is equal to 1, which is when cosine is 1, which is when t is 0. Right? Okay, and here, well, here you see you obtain square root of tangent square, right? So it's tangent, so tangent cancels, so you get the secant. And then here is kind of an integral that one computes in Calc 2, right? But let's do that. So for that, you see one again here one sees that you see the derivative of secant is secant times tangent. So we want to secant times tangent to appear, but then we multiply and divide, but then we fix it because we see that there are some other things that appear. Right? So after fixing everything, we see that we multiply by this 1, and then one sees that on top one has the derivative of the denominator. So the integral becomes the natural logarithm of the absolute value of this one, right, of the denominator. Okay, so one arrives here. Fair enough. Okay, so let's do the evaluation. So here it becomes the secant of the secant inverse. Well, it's just set 0, and then here it goes, yeah, and then in 0, secant of 0 is secant of yeah, sorry, secant of 0 is 1. So here you have 1, and tangent of 1 is 0 because tangent of 0 is 0 because sine of 0 is 0. Okay, so this is 0. So this one is a logarithm of 0, of 1, sorry, of this one, which is 0. So we obtain this. Okay, but you see, tangent, the tangent, we remember, right? Tangent is square root of this, right? Square root of this. So we write the square root, and you see it's second and second inverse. So square root of z0 squared minus 1. Okay, so somehow this minus 1 is this minus 1. Okay, and here, well, we notice that z0 is greater than 1. So we can take out we can erase the absolute value signs. So we are here. And once we are here, then you see that when z not tends to infinity, then its corresponding beta, which is the integral, which is this, right? Because it's this one is the integral, which is this. It also tends to infinity. So here, actually, this is a good definition for all positive real numbers. The fact that this is positive, that this is always positive, and hence the integral increases as z0 increases, tells me that this is increasing. So injective. So this means that this is well defined, right? And now for all positive real numbers. Okay, now for negative, what do we do for negative? Well, we just do this. I mean, we just draw again the hyperbola, and then say, okay, the cosine. You see, when I go to the left, I want the cosine to be the same, and but then the sine, which I measure horizontally now, it's the negative of what I would do in the opposite sense, right? So, okay, so now we have for all positive, for all real numbers. Okay, so now let's continue our analysis for positive real numbers. So what we have is that then beta, you see, since z0 is defined to be the hyperbolic cosine, beta is equal to the logarithm. You see here, I just substitute, right? Instead of z0, I write the cosine, the hyperbolic cosine. Okay, and you see here we have this natural logarithm. So we can take the exponential, and when we take the exponential, the natural logarithm cancels. Okay, and then you see here is the trick. You see, so take this one to the left, right, and then square to get rid of this. So we obtain this equality. When you develop this square, when you expand, the cosine, the hyperbolic cosine square cancels with this one, so you are left with the remaining part of this development, and then minus 1, right, on the right. Okay, and then you see multiply by minus 1, so you get this, so you get plus here, and then solve for cosine, for hyperbolic cosine, right? So here it's 1, and then this one goes to the right, this one goes to the right, and then you divide by 2 times the exponential of beta, and then, right, so we arrive at this well-known formula. Okay, but so you see, to define the hyperbolic cosine of beta, what we do is, with respect to Minkowski's form, with respect to Minkowski's interior product on each tangent space, I take a segment of length beta, so hyperbolic length beta, and when I'm done, I look at the point where I finish, and the coordinates are the hyperbolic cosine and the hyperbolic sine. So I will yeah. So that's how things are defined, and so far I already arrived as a theorem at this. Oh, sorry, this was not a definition. This is a theorem as to this well-known formula. Let's now see what happens with the sine, with the hyperbolic sine. So, so the result we have obtained for the hyperbolic cosine, how the like we got it by parametrizing with respect to z, right? I mean, by taking the parametrization that takes z as parameter, right? So here you can see. So the other parametrization could be by of the same curve, by letting the first coordinate be the parameter and then writing the second coordinate in terms of the first one. So let's do that. So it's the parametrization of the very same segment, that joins 0, 1 to my point y0, z0, or y0, z0, z0. And well, you see the y functions as parameter, and then the other coordinate is written in terms of that y, the first coordinate. So derivative, right? So quite straightforward. So the length of that same segment is then this integral, right? Where here inside of the square root sine is this one minus this one. Right, and of course I'm somehow using implicitly that that this number is equal to both integrals, the previous one here, and also the new one. Right, so this I leave you as an exercise. Okay, in other words, that somehow it's independent of the parametrization. Right? All right. Now this one, then I can simplify to this one, right? I mean, first take a common denominator, right? And then in the numerator we are going to have a one. It's going to be square root of something that has one in the numerator, so that's why we get 1 divided by this square root. Okay, and then to solve this integral, we perform a change of variable similar to the one we performed before. Right? So in the previous case, we used we replaced s with the secant of t. And now we are going to replace s with the tangent of t. So you take the derivative, so quite easy to compute, because tangent is defined as sine divided by cosine. All right, so when you substitute here and you write instead of s tangent, and you write the derivative, you obtain this one. Right? Tangent inverse of 0 is 0. And then here you see here we had this identity. So solving for secant square, we see that secant square is tangent square plus 1. So actually what's here is actually the secant. All right, so this integral becomes simply the integral of the secant. But we already found an antiderivative of a primitive of the secant. Right? We found it here. So here it is. When we were working with the cosine, with hyperbolic cosine. Okay, So take that function and evaluate it in the limits of integration. All right, and you arrive here. So so here I'm replacing the second with square root of tangent square plus 1, and then why? Because when I plug in tangent inverse of y naught there, then I just get y naught instead of this. And then here you see here also. Right? Okay, now the number, this number is positive. This I leave you as an exercise. It's an easy exercise. What would happen if it were not? Well, if you will, non-negative. All right, and so we can write this without the absolute value signs. We write it that way, and you see when we arrive here, then we see, okay, now we can just solve for y naught like we did in the hyperbolic cosine case. So we do it. It's kind of, it's pretty much the same trick, and we obtain that the hyperbolic sine is equal to this, and this means that we proved this theorem, that the hyperbolic sine of a real number is equal to this, right? I mean, here you can argue that I'm doing it for positive, right? Okay, yeah, sure, but then just apply this definition and then it's solved. Okay, so that that's then it for today. So you see, somehow the whole thing was, the whole point was to present the hyperbolic sine and the hyperbolic cosine in terms of the hyperbola, and not defining them through these equalities. Right?